So just give you a very brief introduction. Xianghua, is currently professor at the University of Minnesota, Division of Biostatistics, and she's actually, she actually graduated from Johns Hopkins Biostatistics. Okay, so on record, she received her PhD degree, 2005. I can't believe that. Oh my God, 19 years ago. And Xianghua, the background, Xianghua received her bachelor degree, BS degree from Peking University, one of the best university in China, okay? And received PhD degree from Johns Hopkins Biostatistics in 2005, okay? And she's a professor now, okay? And with expertise, I don't know how to say it, but to summarize, her expertise is slang, okay? Very appropriate, very much matched with what we are interested here. Okay, so I'll turn to you. So today, she's going to give a talk. I think it's going to be very interesting. Very relevant for SLAM group presentation, the two-sample survival probability curves, a graphical approach for the analysis of time-to-event data in clinical trials. Okay, Xianghua?
Sure. Thank you, Dr. Wang, for the very nice introduction. I'm a very applied person, so I have a joint appointment in the Masonic Cancer Center, Biostat Core here in University of Minnesota, and the Division of Biostat and Health Data Science in School of Public Health. So many of my survival-related method work was motivated by applied data, or sometimes just because I was a Bayesian student and student needed topics. So many topics were worked out with students and sometimes co-advisors as well. So for today's talk, it's a joint work with my former PhD student, Dr. Sandra Castro-Pearson, and Professor Chap Lee, who just retired earlier this year, and Ms. Michelle Lieberg, my current PhD student, who is co-advised with Dr. Tom Murray, because Tom Murray is a Bayesian expert. Anyhow, let me give a brief introduction of the background. As we know, time-to-event outcomes are common in randomized controlled trials, RCT. For a brief, the standard procedure to analyze time-to-event outcomes in RCTs typically relies on Kaplan-Meier curve estimation first, and then people provide a log-rank test as an unadjusted analysis, maybe together with the hazard ratio estimate as a treatment effect estimate based on the Cox model. However, based on some literature review and also our own experience in practice, oftentimes survival analysis training, some basic training in survival analysis is needed for people to understand these sophisticated statistical methods, such as how to interpret hazard ratio from Cox model. And oftentimes it's misinterpreted even by some health professionals. So the misinterpretation of some statistical results can impact not just the patient communication with doctors, it can also impact the treatment selection and other maybe higher level, such as a policy making level at the government level. So these issues have been addressed maybe by different methods, for example, providing multiple measures of a treatment effect. or provides depictions of different treatment effect estimates. So some references are provided here, and I believe more references can be found in the paper published in the contemporary clinical trial last maybe 2 years ago with Sandra and Chep. Okay. So now here I want to move to something which is very familiar to people, the so-called ROC curves, receiver operating characteristic curves. Um, so actually, at the beginning of this project, Chep called this work ROC curve project because what I'm going to present is pretty much motivated by the ROC curve in, say, biomarker or screening tests for patients. So I stole this figure from Wikipedia. It's very colorful, but you can see that the typical ROC curve for determining the optimal cutoff for a biomarker for disease screening can look something like this, okay? And in this one by one space, this block, the x-axis is the false positive rate, and the y-axis is the true positive rate. If you don't quite recall what they mean from the EP1 class, it's fine. I don't remember them often, but false positive rate, TPR, is also called sensitivity. And the y-axis, the true positive rate is simply 1 minus specificity, okay? So consider a continuous biomarker. So for a different cutoff, you can find the dot in this space and connect them. You can get an ROC curve. And this blue curve represents a very good prediction of this biomarker, but curves closer to the diagonal are less ideal for this purpose. So in that case, in the epi class, we use, say, D to denote disease status, and D equal to 0 for no disease, D equal to 1 for disease group. And the continuous biomarker, I use Y to denote a positive biomarker. And when it's greater than little y, it's a positive test result. But it's when it's less than or equal to y, it's a negative result. So the formal definition of FPR is simply the probability of the biomarker greater than little y, the cutoff, given this is a non-disease subgroup. Okay, so I use S sub 0 y for this probability because it's simply a survival function, right? Subgroup survival function. Similarly, for TPR, you can denote TPR as also a survival function for the disease groups survival function of the biomarker distribution. And the ROC curve is simply a map, right, from FPR to TPR. If I go back quickly to this, so the ROC curve is a map, right, from X to Y. Okay, more formally, you can express the left-hand side as the ROC is just a function of the non-disease group's survival function of the biomarker variable to the survival function for the disease group. Or equivalently, you can express the ROC function as ROC of U. I mean, if you let S sub 0 y equal to U and solve that equation, the little y will be just the inverse function of x0 at U, right? So you can easily express the ROC curve formally like this. So this is our motivation for doing like an ROC type of curve for survival data, because they are right survival function. So now let's go to the familiar survival analysis notation. Let T denote time to death. Okay, we don't have biomarker anymore. So we have T to denote the time to death, and TRT for treatment. 1 is equal to 1 is a patient being randomized to the treatment arm, 0 for the control arm. So the S sub 0 T is actually the control group's survival function, and as 1T is the survival function in the treatment group, right? So I should mention that we focus on two-arm RCT in this talk and related work. So the two-sample survival probability curve, the so-called proposed two-sample survival probability curve, or sometimes we'll call it survival ROC curve, is defined as a formula R, capital R, to denote this function of the control group survival equal to the treatment group survival, or equivalently, R is simply the treatment group survival function of the inverse of the control group survival at U. Okay, U is between 0 and 100%. So that's the formal definition of the survival ROC, or two-sample survival probability curve. And then the next question is how to estimate the survival two-sample survival curve. Okay, so let's introduce the data first. So we suppose we have IID observations of this kind of triplet. X is the observed time, the typical survival notation, which is the minimum value of the true survival time and a censoring time, and also the treatment indicator. And the delta is the censoring indicator variable. And of course, we need the independent censoring assumption as usual. So we use hat as hat to denote the Kaplan-Meier estimator of the survival function for the two group, the control and the treatment group. And the nonparametric estimator of the two-sample curve can be proposed like this. Okay, it's simply plugging in the Kaplan-Meier estimator into the corresponding place for the true survival function. So how to draw the curve in this one by one space? Okay, we start from the upper right corner, 1, 1 point. So suppose we have this toy data. I forgot whether this data was taken from textbook or just made up by Sandra, but it's a very small data set. If you sort the unique survival time, not censoring time, just survival time, T sub 1 parentheses, just the smallest, right? That's time, 1.5, and then keep looking. Next one is 2 in the treatment group, right? 1.5s are all in control group, and then 2 in treatment group, so on and so forth. The last death time is 7 in the treatment group. Okay, and everyone knows how to calculate Kaplan-Meier within treatment group. And this is a little table for that hand calculation. The risk set size, the event, number of events at the unique event time, number of censoring cases, and the survival probability estimate. Okay, so as we know, the survival estimate, the Kaplan-Meier estimate start from the 100% point. Here we start from 1, 1 point. And then the first death time is 1.5, and 3 of them all occurred in the control group. So I should mention, that the x-axis in this survival ROC plot is the control arm, and the y-axis is the treatment arm. So so we need some imagination here. So the bad thing happened first in control group. So the control group survival curve drops first, right? So this curve should go horizontally to the left first, okay? Because this axis, x-axis, is the survival probability of the control arm. So the control arm survival probably drops from 100% to like 0.7. And the size of this jump is from the Kaplan-Meier estimator, right, for the control group. So we just use whatever is available from a Kaplan-Meier table here. Okay, then the next drop. So the next event time 2, two is from treatment group. Not in the control, just one case in treatment group. So the A should be a vertical line, right? So now if you look at second entry of these pairs, so the drops should be from, right, the larger value to the smaller value, 100% to 90%, which can be found from here at the first drop in the treatment group. You can keep doing this when the death time, the unique next unique death time occurs only in one group. However, in the next case, 2.5, we see both groups having death events, right? 2.5 at 2.5. And so where should we go? We should go both horizontally and vertically. Then we choose to go diagonally. So the jump size again is determined by the jump size in their respective Kaplan-Meier, one sample Kaplan-Meier estimator. Okay, so those are like 3 cases, and the rest are just a replicate of one of those 3 cases. Oh, sorry, Dr. Wang, I saw you were talking, so you were muted. Do you have a question?
So any question? So, Xianghua, may I understand the curve from the perspective that because you are really using a composite function of S now and S1, because we understand the survival curve, the area under the curve is the concordance probability. Concordance probability of 2 survival time. Survival time for treatment group, survival time for control group. So you can sort of think of, control. Oh,
I have a slide down here.
Yeah. So you kind of control T a little bit. And then you look at the concordance of the 2 groups to figure out the interpretation.
Yeah, if I understand your question correctly.
Right,
so
right.
the area under the curve, if you calculate the integral of this curve, it should be a concordance probability. It has a very good physical meaning. And also the similar interpretation as a traditional RLC curve. When you see a curve departing from the diagonal, it means good. In this case, the treatment has a bigger benefit than control. And maybe the area in the curve measures the magnitude of that treatment effect. But I will talk a little bit about the difficulty in estimating concordance.
Okay.
So in this case, it's very ideal, right? You have a complete ROC curve, meaning that, if you keep drawing, it should reach 0, 0. So the curve is complete from 1, 1 to 0, 0. But in some other cases, I will show one example, a bone marrow transplant data example. Because of the heavy censoring, you cannot reach this dot. So making the integration of the estimated curve not necessarily a good measure of concordance. So but in this paper we try not to avoid that because that's difficult to answer. So we focus on the graphical feature and the advantage of using a graphical method as an additional tool in our survival analysis toolbox rather than replacing any existing treatment effect measure or models. Okay, and any other questions? Okay, let me move on to the next slide. So these are three data sets that we use to illustrate this method. Maybe I should talk about the bone marrow transplant data first because I already mentioned it. So typically, we in a main outcome paper of clinical trial, we present two survival curves, right, for two-arm trial. However, in our proposed approach, you only need to present one curve. Maybe the benefit is not that obvious, but when I continue to talk about effect modification, this decreased dimension feature will give us some advantage. Okay, so in this case, we see censoring, a lot of censoring. So the curve, the non-parametric curve specifically, we cannot use the integration of this non-parametric curve to get a good estimated concordance because the non-parametric curve, the Kaplan-Meier curve, as we know, is not defined beyond the last event time. So, but in the other two cases, we have got complete curves. So this is a very famous textbook example, 6MP versus placebo trial, a survival textbook example. So we see a clear separation in the survival curve here, in this traditional Kaplan-Meier curve plot, and also a departure of the estimated curve from diagonal. Okay, here a little bit tricky because we first see a benefit of a treatment and then that benefit seems to disappear. So any questions about these data examples? Okay. So a little summary of the properties of the non-parametric method for the sensor data. So as we can see, all trials will be standardized to this same space, regardless the follow-up time, the censoring, the length of censoring, etc. And secondly, the two axes are easy to understand as they are survival probabilities. Right now, like in ROC, we need to check our textbook, epi textbooks, remember what they are. Here it's very clear the two axes are survival probability. And to make a visual test of the treatment effect, you can compare the curve with the diagonal line. So I have mentioned that the closer the curve to the top left corner, the more benefit the treatment provides as compared to the control. On the contrary, when the curve is closer to the diagonal, we know that it's less beneficial. And the other extreme would be like the treatment is even worse than the control, right? If the curve is found in the bottom half of the space. Okay, and also we can provide a common visual reference for the non-effect across all types of all trials. Okay, so I already mentioned that. Numeric integration of the non-parametric curve can lead to some similar afference concordance. But since the censoring problem, we actually didn't suggest to use our curve for that purpose in the paper, but we provided a reference about different afferent concordance estimators when there are censoring. But since that's beyond the scope of that clinical trial paper, we didn't go very further on that topic. So in addition to visualizing treatment effect, we also found that the proposed method can help with detecting potential effect modifier. For example, the simplest case would be probably the two-factor case, right? Suppose you have a covariate with two levels. A standard graphical approach would be comparing, say, two levels per treatment arm. That will make four subgroups, right? People will present four Kaplan-Meier curves in one plot. I've seen that a lot in, say, cancer research papers. And they can immediately get difficult when you have more levels, say, for cancer stages. For two treatment group, you will present 8 curves. So it will be very busy in Kaplan-Meier curve plot. Using our method, we can synthesize these many subgroup Kaplan-Meier curves into half many two-sample survival curves. So here is what I mean, right? For the bone marrow transplant data, again, we plot the survival probability of one treatment arm, which is a peripheral blood group, versus the bone marrow transplant group. So, but we stratify the data to two groups, male and female. So you here see the solid line for male group and the dashed line for female subgroup. And in here, visually, you probably can draw a conclusion that there's no much difference in terms of treatment effect. So that's a evidence of no significant effect modification by this factor. Okay.
Sorry, I'm interrupting. The previous graph is very interesting. Is there a way to give a quantified, every time you show such a graph, the next question is, in this case, it's clear. What if it's a borderline difference? How do you identify that? Is there a quick summary information?
So to quantify the difference, again, it's impacted by the censoring for this specific this data set. If you say want to use area under curve or area between the estimated curve and diagonal line for each treatment arm, and even the area between the two subgroups estimated curve, it's doable. But Yifei may have a better idea on that, because we talked a lot about Sandra's other paper, right? How to measure the area between curves and area under curve. But we for this data, this kind of data with heavy censoring, we don't have a suggestion for for a numerical measure. Yeah. And now you may wonder, how about the model-based method? We talked about non-parametric estimate of the RLC survival curve. What about the model-based? So I use Cox model as an example, but of course you can derive, say, accelerated failure time models to sample survival curve. My student actually did that in the first draft, but we didn't include it in the final published version. So let's look at Cox model together. The very familiar hazard function. And so if I could hide the blue part first, it's easily proved that the survival of the two treatment arm has this nice relationship. Okay, because this is just as the simple Cox model with a two-arm covariate. Nothing time changing or anything. So you have this nice relationship. And by looking at this equation, it's just the RLC curve, right? Because means survival function in the treatment group is a function of the control group survival function, right? That's exactly the definition of the RLC survival curve. So I put this part on the left-hand side so you can see clearly now. If you equate this, the blue notation, and this, it's just the definition of a Cox model-based curve. Okay, so everyone knows how to estimate the unknown parameter in Cox model in this case. So, I should say that lambda is just an exponentiated beta. Beta is the familiar treatment hazard ratio. Sorry, log hazard ratio interpretation, and this lambda is just a transformed beta. So the Cox-based two-sample survival curve estimate is then I use 2D to distinguish it from the nonparametric curve estimate. It's just the U to the power in the Cox model estimated lambda hat, which is exponential beta hat. Okay, and the area under curve. So now I can talk about area under curve, because I mean it's not impacted by the censoring problem. Basically, when you have a data like the BMD data set, you can do how to say extrapolation, right? By using this form, this functional form. So if the Cox model is true, then the area under curve based on the Cox model is simply a function of the unknown parameter, exponential beta. So you can easily prove that 1 over lambda, which is just exponential minus beta, right, can be interpreted as a odds, right? It's an odds. So probability divided by 1 minus probability, and these can be found in literature. Basically, they are not invented by us. So for Cox model, there are nice interpretation of the area under curve and the relationship between area and curve, and the regression coefficient, and the regression coefficient function has the odds interpretation. But these all depend on the Cox model assumption, the proportional hazards assumption. And those nice interpretation will go away if the proportional hazard assumption is not met. So a natural question would be, how to use the proposed graphical method for a model diagnosis purpose. So a quick way is just to overlay, right, the Cox model-based curve on the nonparametric two-sample curve. So it's probably not easy to look at this, but for the first study, we can see that the model-based very smooth curve goes through the nonparametric two-sample curve estimate. Okay, I will say the second case data example they also are very close to each other. No evidence of pH violated pH assumption. However, in the third case, the nonparametric curve is the step function, but the model-based Cox model-based curve is pretty much mixed with the diagonal. And that's not the truth. Of course, you can say improve the model, but this plot exactly tells you that the simple Cox model is not a good fit of the data, right? So you can maybe use a change point Cox model to improve the fit. That's the help message from the graphical method that we propose.
So Xianghua, I have a question about those curves. So I just wonder, when you do testing, hypothesis testing, it would be very interesting to see the violation of Cox model, like crossover of a hazard function. You have crossover of two hazard function, then implies the Cox model wouldn't be valid. So I just wonder if the curve you propose here can, for example, can it detect crossover in hazard? Something like that. I'm just trying to think of the usefulness of your, the proposed ROC curve.
Yeah, basically talking about crossover. The crossover of the two-sample curve with the diagonal line coincide with the crossover between two survival curves. That's
So you could have a crossover in two survival curve, and that would be really bad. But you could also have crossover in hazard function.
Right, exactly. So with this plot or the Kaplan-Meier plot cannot help much with visualizing the crossover hazard function.
Okay, but it visualize crossover in survival function.
Correct. And in the paper, I didn't include that the figure in the slide, but in Sandra's paper, she presented some other graphical model diagnosis methods results together with our diagnosis plot. I found that in the case data example that she found, our model can easily let people see that there is some violation, but the comparison method, the residual based method, she saw very similar plots based on the other method. So again, the focus is still on visualizing the model fit, no like numerical measure or a formal testing p-value kind of thing from this method. I think the rest of the time I will switch the gear, but before doing that, any more questions about right-censored data to sample survival curve? Okay, but the next work is ongoing. Actually, Sandra is going to submit this second paper, the two sample survival curve beyond right censoring, hopefully in the next few weeks. So it's a straightforward extension of the right censor work that we did in the first paper. And instead of Kaplan-Meier estimator for right censor data, we can use non-parametric MLE estimator for other types of censoring or truncations, right? But maybe in any survival textbook, the first chapter will talk about all kind of censorings or truncations. I'm not going to have a slide about that. But remember that due to the unique structure of different types of censored or truncated case, there could be certain undefined portions in the survival curve estimate, right? And similarly, for the two sample curves, we will have an undefined portion as well. So just carried from the one sample estimator. Okay, I remember that when I was student, Dr. Wang referred me to this author's seminal work about self-consistency algorithms. Basically, that's just an example of EM algorithm to obtain the non-probability MLE for arbitrarily censored and truncated data. And in this second work of ours, we extended, Turnbull's method and some other authors' method for different types of censored or truncated data to the two sample graphical method. Specifically, we extended the proposed method to interval doubly or doubly interval censored data without truncation, or the singly truncated and singly censored data. There are more complex situations, but in practice, it's hard to find examples. That's one of the reasons we didn't for many cases, because it's hard to find examples. But you can refer to those newer work for the one sample estimators. And in the next few slides, I will just show the special cases that I just mentioned. First, I want to extend the right censor method to the graphical method for interval sensor data. So in the textbook, we can find different types of interval sensor data. For the first, the so-called mouse study, all animals in the experiment died or were sacrificed and assessed for their tumors after they died or sacrificed. So this is an example of type 1 interval sensor data, because if tumors were found in the mouse at the observation time, then it's left censored because the event occurred before the sacrifice time or death time. Otherwise, it would right censored. Right? And the other interval censored data example is from a breast cancer study comparing time to cosmetic deterioration. So this is the time variable of interest. And it's called type M interval censored data because assessment of this condition, the deterioration, occurred every few months. And for each patient, the event occurred in intervals like this, right? L for left, R for right. And I'm not going to show you the nonparametric MLE's estimators form, but this is the result, the graphical result. So in the left panel, the animal study, the right panel, the breast cancer study, and in a typical mean survival analysis paper, you will see like the two groups survival curve estimate, but we consolidate them into one two-sample curve. And there are undetermined boxes here, as you can see, for both data. And probably you can say that for the, it's probably due to the rare data, it's hard to interpret this. But here, this arm, shows some beneficial effect at a later time point than earlier time point. And this is a doubly interval sensor data. By doubly interval sensor data, we mean that the event time that we are interested in may have both the start, the initiation event and the event of interest being interval censored. That's called doubly interval sensor data. In this case, the HIV positive test time and the AIDS symptom onset time are both interval censored because they were only recorded in 6 month intervals. So this is the two sample curve using a data set that Sandra found online. That's not our study. Only the BMT data I actually have worked on myself. The other data sets were all from the internet or textbook. And I believe this is the last example. This is a textbook example. I just want to show something about truncation. It's the left truncated right censored data. Canning House is a aging center, I believe. So there is the left truncated data problem because people need to survive long enough to get into this aging center. Otherwise, they won't even be observed. So there is a life truncation problem. And the right sensor ring is just a typical right censoring in many follow-up study. And this is the estimated bivariate curve. Okay, so quick maybe summary. This is probably the last few slides. The proposed graphical method can be extended to other types of univariate time to event data that is not covered in this talk, as long as a proper survival estimator is available. So I put this dot here to maybe showcase one of my students, different students' work. In that work, we studied component-wide censored composite survival endpoint data. Say relapse-free survival. The relapse time is interval sensor, but death is a standard right sensor. So we propose a non-parametric estimator for that kind of data. Just as long as you can find a proper survival estimator for the one sample case, you can always put them together into a two sample curve. Okay, and also regardless of whether the one sample method you found is nonparametric or semiparametric, such as Cox model, accelerated filter time model, or even parametric model like Weibull, or regardless it's a frequentist method or Bayesian method, I mean, we can always put a two sample survival curve together. So actually, the next the third work in this research is a Bayesian model work, because my the student co-advised by Tom and I were interested in Bayesian survival. I am a survival non-Bayesian person. Tom is a Bayesian survival, and he knows a lot of things. I mean, and not just Bayesian, but we co-advise the student to extend Sandra's two sample curve paper to a Bayesian model. I mean, there are a lot of advantages in Bayesian modeling because I mean, the treatment effect can be very flexible. We don't have to have a assumed form like Cox model. And also we can draw inference for a complex statistical functional such as the AUC. Maybe I can quickly go back to the definition of AUC in one case, right? So it's just AUC is just a functional of the survival functions of two treatment arms. Or maybe there are other difficult functionals, but the Bayesian models have the advantage of draw statistical inference for such situation. Also, I want to mention that the proposed method can be extended to observational studies by using maybe causal inference techniques or say adjusted Kaplan-Meier curve. So I actually the second work, the beyond the right-censoring work, I mean, it's already hard to advocate this method as for randomized trial already, because truncated data is probably not from the Canyon House data is not from randomized trial. So, I mean, there might be a intersection between causal inference method and this graphical work worthwhile to explore next. And also the last thought, which is a very wild idea. I have no solution, but there are multiple arms oftentimes being observed in clinical trials, like 3-arm trial. What do we do with 3-arm trials? Well, first, we can do pairwise comparison for like 3 times for a 3-arm trial, but is there a better, more elegant solution, like 3-dimensional ROC curve or surface? Probably is the right word. I have no solution. I mean, that's just a discussion point. Yeah, I believe that's the end of the talk, and put some key references just for this talk here, but there are more references can be found in the papers, and these are. Oh, sure.
Yeah, sorry. No, I mean, it's just, I saw all the extensions that you have done. I'm just getting out of DSMB meeting on adaptive clinical trial. So how do you, I mean, is there going to be any significant change in how you compare the survival curves when you are in an adaptive design scenario?
Oh,
I know it's far-fetched. It's just I'm putting in critiques.
that's interesting.
The analytic plan doesn't seem to have it. We can talk later, but it's just something that was, I saw all those extensions. I was just thinking,
Yeah,
I love the graphical comparison. So, I mean, I was just running out of a DSMB meeting for this. So, and that's an adaptive clinical trial. So it's quite, I mean, this comparison is quite graphical pictures. I do like it, conveys a lot more than other setup. So, and it's simple, intuitive in understanding. So just food for thought, nothing else.
Thank you.
Mhm.
Yeah, as you can see, we only deal with the simplest case, two-arm
Yeah.
randomized trials. Yeah,
Yeah.
that actually, even I were working with Sandra on a different curve, also two sample curve problem, but not survival curve, but cumulative incidence curve for competing risk data. I mean,
Mhm.
due to the work pace of the student and everyone. I mean, that topic is still in work in progress. So, I mean, that's another direction of
Mhm. Mhm.
research based
Mhm.
on this work.
Mhm. Mhm. Because I thought because you had a nice stratified, you reduced the number of curves down to 4, right, for effect modification. I was
Mhm.
thinking in the adaptive scenario, some such thing can be done. So that's why that curve was. So it's just a timely talk. Mei-Cheng, you always arrange great talks.
Thank you for the nice word. Yeah, I mean yeah, last slide, as I told Mei Chen before the seminar started, thanks to my very talented PhD student, Dr. Sandra Castro Pearson, and current student Michelle Lieberg. They are very strong in computing and writing and everything. And this original idea was from Dr. Chep Lee, and mean they mean Michelle got a lot of help in terms of Bayesian computing, which I have no idea. So I mean, very talented people in our team making this work possible. So I just like to thank them and everyone here to listen to this talk. It's the first time I present uh, this work, this sequence of work. So it's a very it's a big pleasure for me.